In this video, we're going to talk about building models with multiple predictors, and we're still talking about linear models here. So the data set we're going to work with for this video is called Allbacks. It's from one of the R packages, and it basically has data on 15 books. So a small data set that you can see here on the slide on the volume and weight of them. And we also happen to know if the books are paperback, that's denoted by PB, or hardback, that's denoted by HB. The volume is measured in cubic centimeters, the area in square centimeters, so we're not going to work with the area variable here, and the weight is measured in grams. So this is going to be important, the units of measurement, when we get to interpreting the coefficients. Let's fit our model. So first we're going to start with a simple model. We're using the linear reg function to get our linear model started. We're setting our engine to be the linear model, and then we're defining how we want to fit our model, weight versus volume, and the data set is called Allbacks. And here is a tidy output of the regression. We can see a positive slope based on these points on the scatter plot, and in fact we see a positive slope in the model output as well. So that's 0.709. The way we would interpret this is every additional, so for each additional cubic centimeter, the book's volume is bigger, we would expect the weight to be higher on average by 0.709 grams. And the 108 number is our intercept. So when volume is 0, so for books with 0 volume, we would expect their weight to be 108 grams on average, which doesn't make any sense in context, but it doesn't make sense because it's actually an extrapolation. If we look at our scatter plot, our book volumes go somewhere from maybe 400 or so cubic centimeters to about 1500. 0 is nowhere nearby. So that would be extending the line to extrapolate all the way down to a volume of 0, for which we don't have any data anyway. So we would never expect our predictions in that area to be reliable. And in fact, the intercept is not. Mathematically, it again serves to adjust the height of our regression line, but in context, it's not a useful number. Now let's do something else. So now we've added cover information to our visualization. So you can see that going from the earlier visualization to this one, we have actually now changed the colors and the shapes of these points. So we're seeing the hardback books and the paperback books here. The hardbacks are in like orange and in circles, and the paperbacks are in purple and in triangles. They're represented by that. In terms of our model, the only thing that has changed is how we actually define our explanatory variables. So we have gone from our only explanatory variable volume to volume and cover. And we're basically fitting this model with these two explanatory variables, and so we separate them by pluses. If we had 20 explanatory variables, we would separate each one of them with pluses. Now, what happened? The slope of our volume changed a little bit, and now we have a new slope for the cover variable as well. And then I can see this PB right next to it. So the variable that we're using from the data set is called cover, but in the regression output, we're seeing cover, but then also PB right next to it. So that's what we talked about in terms of dummy variables earlier. The hardback level, which is the first level that comes alphabetically since we haven't done any sort of manipulation to it. So hardback is our baseline level. You can think of that as the 0 level, and then paperback is the other level that we're working with. So basically that negative 184 number tells us what the expected weight difference is for books that are paperback compared to hardback. And when we say paperback compared to hardback, we would expect paperback books to weigh less, so that negative number does actually make sense. Let's go through and interpret those numbers though. So I have the model output from the previous slide here again. Let's start with the volume for slope. So that's the 0.718 number. All else held constant, and we'll get to that phrase in just a second, all else held constant, for each additional cubic centimeter, books are larger in volume, we would expect the weight to be higher on average by 0.718 grams. So the second half of the sentence, for each additional cubic centimeter, and this is what we would expect to happen to the response variable on average, just like we've done before. But we have this new bit here that says all else held constant. So what does that mean? In this case, all else is basically just the cover variable. So basically saying that either we have, if we're thinking about hardback books, we're only comparing them to each other that are different in their volume, or if we're thinking about paperback books, we're only comparing them to each other that are different in volume. But we are not comparing a book, let's say, with comparing the predicted weight of a book with a given volume that's hardback versus paperback. So when we're interpreting these coefficients, when we have multiple variables, each one of these numbers that are our slope estimates from the model output are going to be interpreted assuming everything else, all the other explanatory variables in the model, are held constant. Can we assume that this is realistic? Is it possible that a book's volume grows without its paperback or hardback status changes? And obviously thinking about an individual book growing, it's not a child, it doesn't make any sense. But let's think about two separate books. One is hardback and one is paperback. Is it possible that they're different in volume? Absolutely. It is possible. So it is quite possible that the volume of a book is independent of whether it's hardback or paperback. We're not using this model to decide any sort of independence, but in this case, it might make sense to think about these two variables changing independently from each other. Sometimes it's not really possible to think about that. So if you think about, for example, likelihood of it raining and humidity, they don't really go entirely independently, right? So there you can think of building certain models where you have explanatory variables where it would be really unlikely for your explanatory variables to change independently of each other. So when we're interpreting these models, this all else held constant is always something that we do actually have in our mind, because that's what those coefficient estimates are. And sometimes we might need to be critical about whether that assumption is reasonable or not. Let's look at the other one for the cover. So for cover, that estimate was negative 1.84. So what that means is that all else held constant. So think about it as we're thinking about books with same volume. Paperback books weigh on average by 184 grams less than hardcover books. And finally, the intercept is hardcover books, so that's our 0, with 0 volume, are expected to weigh 198 grams on average, which doesn't really make sense in context. So hopefully the 0 volume part of this interpretation is a little bit more intuitive, but how did I know that we're talking about hardcover books and not just any type of book or not paperback books? You want to think about plugging in a 0 for each one of your explanatory variables. Plugging in a 0 for volume, which is already numerical, fine. Plugging in a 0 for cover, it's a categorical variable. What does it mean to plug in a 0 for it? Well, it basically means that you're thinking about the baseline level. So plugging in a 0 for the cover variable basically means we're talking about the baseline, which is the hardcover. So let's talk about now this notion of main versus interaction effects. Suppose we want to predict weight of books from their volume and their cover type, so hardback versus paperback. Do you think a model with main effects or interaction effects is more appropriate? So what do I mean by this? Main effects would mean rate at which weight changes as volume increases would be the same for hardback and paperback books. And interaction effects would mean that the rate at which weight changes as volume increases would be different for hardcover and paperback books. So would we imagine that for these two different types of books, as volume grows, how much their weight grows would go at the same level or at different levels? How would we decide this? I want you to think about this for a second conceptually, and then we're going to take a look at the data. All right, here are the two pictures that we have. On top, we have the main effects. So in this case, what we're saying is that, remember, the orange line is the hardback and the purple is the paperback. And those lines are parallel to each other. So as volume increases, weight is increasing at the same rate for both these types of books. In the bottom plot, we actually have the parallels the lines not parallel with each other. And I think the distinction is so minor that you do need to look a little bit closely at it, but you can see that the orange line is a bit steeper than the purple line. So here, as volume increases, the rate at which weight is changing is slightly different for two types of books. So which one of these makes more sense? Just looking at the data. Maybe hard to say. So why do we care about this? And here comes the idea of Occam's razor, which you may have heard about from other contexts. It states that among competing hypotheses that predict equally well, so that's important, that predict equally well, the one with the fewest assumptions should be selected. So basically saying, go for the simpler explanation. Model selection follows this principle. So here we have two models we're looking at. Should we consider interaction effects or should we consider just the main effects? And model selection tends to follow this principle. We only want to add another variable to the model if the addition of that variable brings something valuable in terms of the predictive power of the model. In other words, we prefer the simplest, best model, and a term we have for that in statistics is the parsimonious model. So, looking back at that same picture, visually, which of the two models is preferable under Occam's razor? Which of the two, the main effects on top or the interaction effects in the bottom with the different slopes, does a better job at predicting the book weights? A little bit hard to tell, I think, just by looking at it visually. So we actually turn to some measures that would be useful for us in order to make this sort of decision, or really at least to start thinking about it. One of the statistics that we care about is called R-squared. So R-squared is the percentage of variability in the response variable that's explained by the regression model. And we can grab the R-squared of any model using the glance function that actually will spit out a bunch of statistics that might be useful for us. One of them is R-squared, so we can actually grab that just by accessing that element out of the glance object. So we can see that the R-squared for the model with the main effects is 92.7% roughly. And for that one with the interaction effects, it is 92.9. Okay, so the one with the interaction effects is able to explain a higher percentage of the variability in the response variable. Maybe that means it's better. We're going to take a look at that. But before we move on, let's talk a little bit about what does it mean to explain the percentage of variability in a model. So let's think about it this way. By the end of the semester, you're each going to get a score, like a grade in this course, right? And not every single person is going to get the same grade. So we're going to have a variability. If I have a data frame with your names down the rows and a column of final scores in the class, we're going to have different numbers for each of the students, right? Maybe some overlap, but generally different numbers, which means that there is going to be some variability in this variable of your final scores. Some variability meaning that if I was to calculate its standard deviation or variance, I'm not going to get a 0. There is some deviation from the mean in your scores. What explains this variability? What might be the reason for some students scoring higher and some students scoring lower? We might imagine how much they studied. It's probably a good indicator. Do you think it explains everything? Maybe not necessarily. How many credits they're taking this semester? So maybe we want to consider both how much they studied for this particular course and what their workload in general was for this semester. What their living situation was, given that everything is online, what their internet connectivity was. It's possible all of these are ultimately having an effect on how you perform in a class and how much you enjoy the topic, how much you've been doing the work, and many other things that you can think about. So we can think about all of these variables that would contribute to us being able to explain the variability in our response variable, which in that example is your final score. So we can think about building a model where I collect all of this other information from you. And I realize that some of them are hard to measure. How much you enjoy the class on a scale of 1 to 10, it's going to be hard to measure. But let's imagine we collected that data and built a model. And so R squared of that model will basically tell us what % of the variability in your final exam scores can be explained by the model that includes all of those variables that we collected from you. You think we'll be able to explain all of it? My guess is no. I think that even if we, brainstormed for hours and thought about what might be all the reasons why students score differently in a class and built a model based off of all of those variables, and even if we lived in a perfect world and assumed that we really can measure these things like your enjoyment and stuff like that, even then, chances are we're not going to hit 100% for our R squared, because the thing is, there's probably some randomness in there as well. So we would like our R squared number to be as high as possible, as close to 100% as possible. But chances are it's going to be something that's a lot lower than that. And these numbers we're seeing here, over 90%, that's probably pretty hard to achieve in nature. I mean, this is real data, and there we are actually able to see that. But it's probably that these are a particular type of book. I think it said earlier on, I didn't mention it explicitly, but if you look at the package documentation, these data come from books on the shelf of a professor. So they're probably very similar scientific textbooks or something like that. It's not even like kids' books mixed in with adults' books. So chances are, actually knowing the volume and whether the book is paperback or not tells us a lot about its weight. But if we had, a data set with like all different types of books, some children's books, some art books, some coffee table books, and some like novels, paperback novels, then I think that the R squareds would be potentially a lot lower. So in general, we want a high R squared, but it's not always easy to achieve that. So in this case, clearly the model with the interactions has a higher R squared. However, using R squared for model selection in models with multiple explanatory variables is not a good idea, as your R squared will increase when any variable is added to the model. I could have added my mom's age to this model and R squared would have increased, which obviously has nothing to do with the weights of these books. So then what do? This R squared is an informative statistic, because sometimes we actually want to know the percentage of variability explained, and that's when we turn to R squared. But when we're comparing models with different numbers of variables, or when we're comparing models, period, that is not actually what we want to be looking at. So instead, we want to look at what we call adjusted R squared, which is a more objective measure for model selection. Adjusted R squared doesn't just increase if the new variable does not provide any new information or is completely unrelated. Think about adding my mom's age to the model, as it applies a penalty for the number of variables included in the model. So while R squared would increase, adjusted R squared would then apply a penalty for that additional variable. And if the increase in R squared was pretty minor, because it was a pretty useless variable, then probably that penalty would not have been outweighed by that tiny increase. So this makes adjusted R squared a preferable metric for model selection in multiple regression models. So let's take a look at these. On one side, I have the R squared values for the main effects and the interaction effects models. So these are the numbers that we saw earlier. And then on the other side, I have the adjusted R squareds, which I can again use the glance function to extract them out. How do these two compare? So for the main effects model, my adjusted R squared is 91.53 or 54. And for the interaction model, my adjusted R squared is like 91.05%. So which one is higher? Is R squared higher for the interaction model? Yes. But is adjusted R squared higher for the interaction model? Actually, no. So in which case, we're basically saying that we probably don't need to overcomplicate this model and add the interaction effect, which maybe was a little bit, maybe not entirely, but may have been your hunch when we looked at those two visualizations earlier, where we looked at the parallel slopes, and then we looked at the visualization with the different slopes, and they were barely different from each other. So it's not like these models are doing something entirely different and fitting these data. And so then why overcomplicate by adding the interaction effect? So hopefully in this video, using this small data set, we were able to touch on a few important topics. What's R squared, which is the percentage of variability in a regression model that's explained by the model, so all of the explanatory variables in the model. Adjusted R squared is that number, but adjusted for the number of explanatory variables in our model with a penalty for more variables. So that's what we use for comparing models to each other. And we've also talked about fitting multiple regression models, both in terms of the R syntax and also interpreting the regression output, with the most important aspect of that interpretation being that when we're interpreting these regression coefficients for multiple regression models, we're thinking about all else held constant and interpreting only one variable at a time.